IEC 61131-3 is the international standard that establishes the rules of PLC programming. In this complete video course, we are going to explore all the aspects that the standard defines. If you master these concepts, you will be able to program PLCs effectively, no matter what brand you are using. To truly appreciate the significance of this standard, it is necessary to understand the context from which it emerged. Each prominent PLC manufacturer developed its own proprietary hardware platform and, more importantly, their own unique programming software. This included custom languages and data representations that did not work with anyone else. This led to many challenges for PLC users. First, vendor lock-in. After specializing in one system, switching brands was incredibly difficult. It required a substantial reinvestment in hardware, software, and mainly training. Second, difficulty in integration. Integrating these different systems into one factory was exceptionally difficult. And finally, no code reuse. The absence of a common programming framework made it impossible to reuse code, solutions, or best practices among different brands. This is when the IEC, the International Electrotechnical Committee, stepped in to bring order to this chaos. In the early 90s, they released the IEC 61131-3 standard. This document established a set of core elements for all PLC manufacturers to follow. While the standard covers many details, for us as programmers it can be divided into three core elements. Number 1. It defined a formal software models for organizing PLC application code. It defined the three types of program organization units, also known as POUs, in which a programmer is supposed to write their own code. These units are known as programs, function blocks, and functions. We will dedicate a full video to the differences between these, but just know that the standard dictates how we structure our logic. Number 2. It defined the data model for the precise declaration of variables. The standard defined two key distinct aspects that must be specified for every variable. The scope, or visibility, this means where the variable is declared and how it can be used. Is it a local to one block or global for the whole machine? Is it an input or an output of a specific unit? The data type. This defines what kind of data is represented, like being a simple boolean, an integer number, or a real floating point value. Number 3. It defined a set of programming languages to be used when programming PLCs and creating POUs. The standard today features 4 languages. Ladder diagram, a graphical language that resembles relay wiring schemes, very popular in the US. Structured text, a very powerful high-level textual language with its roots in Ada, Pascal, and C. Function block diagram, a graphical language that is expressed through the interconnection of graphical blocks. Sequential function chart, a graphical language that resembles state machines diagrams. By standardizing these three areas, software models, data, and languages, the IEC gave us a universal toolkit. In the next videos, we will explore these three aspects of the standard in detail and create the foundations for building PLC applications. If you want to dive deeper into the history and details of the standard, check out my book PLC Programming for Beginners on Amazon. Now we are going to explore the first aspect defined in the standard, the software model and program organization units. The standard provides a hierarchical framework for organizing PLC application code. At the highest level, we have the configuration that encompasses the whole system setup. Below are resources, the actual CPUs that run your code. You might have one or more CPUs in your system. The resource manages tasks. The task is the scheduler. It defines the execution context. It tells the CPU to run a specific piece of code, either cyclically, for example every 20 milliseconds, or based on some event, like an interrupt. The code itself is written inside Program Organization Units, or POUs. The standard defines that every programming unit has two distinct parts: the declaration, where inputs, outputs, and internal variables to a programming unit are defined, and the implementation, where the actual logic code is written. The standard defines three distinct types of program organization units. Choosing the correct one is not a matter of preference, it is a matter of software architecture and memory management. First, we have the program. Programs represent the main executable entities within a PLC application. They are the only program organization unit that can be directly invoked by tasks. Programs can also be called by other programs, and another important thing is that programs have state retention, meaning that their own local variables will retain their values between consecutive executions. This allows programs to manage sequences, accumulate values, or maintain information over time. They actually have memory. A program is unique within the PLC application. You cannot create multiple copies of a program linked to the same code. When you create a program, it is instantiated and can be called by tasks or other programs directly. In the default CodeSys project, a program called PLC PRG is created and is called directly by a cyclically scheduled main task. If you want to add a new program to your PLC application, right-click on Application, select Add Object, and select POU. In the menu popping up, you can select Program and choose a name for your program. You will see a new program appearing in your device's tree, in which you can write your own logic, your own declaration and implementation. Then you can either call this program from another program, or call it from a task in the task configuration. Then we have function blocks. This is the most critical component for modern modular programming. Like programs, function blocks are stateful. Their variables needs to be allocated and retained through multiple scan cycles. But unlike programs, function blocks are not meant to be unique. Think of a function block definition as a blueprint. To use it, you must create instances or copies of that blueprint. Each instance will have its own independent set of variables, meaning it will have its own memory and state. Function blocks are the equivalent of classes in traditional object-oriented programming. Through this mechanism, it's possible to reuse logic to control multiple occurrences of the same kind of object, for example, an asynchronous motor. You can reuse the same code by creating multiple instances of it. In this way, you can achieve modularity and efficient design. Adding a function block to your project in CodeSys is similar to adding a program. Just right-click on Application, select Add Object, POU, and select Function Block, and choose the name of your function block. Then you can write your own logic in it and create one or multiple instances of it and call it in other POUs. Then we have functions. They are the simplest type of POU designed for executing specific reusable algorithms. Functions can be called by programs, function block, or even other functions. Crucially, they have no state retention. They do not possess internal memory that persists between calls. Any variable inside a function is temporary. It is created when called and destroyed when finished. Use this for mathematical calculations, conversion, or for logic that should always return the same result given the same inputs. To add a function to your devices tree, you right-click on Application, select Add Object, POU, and select Function, and choose the name of your function. When you create a function in CodeSys, notice this extra field, Return Type. Unlike a program or a function block, a function is meant to return a specific result, like a number or a boolean, directly to the caller. You can write your own logic in your function and call it from whenever you like to run the calculation and return the value that you need. To summarize, use programs to organize the main sections of your machines, use function blocks for devices like motors or timers that need memory, and use functions for pure calculations. Before we move on, let's do a quick reality check on how manufacturers actually implement this standard. For PLC manufacturers that either use CodeSys as their IDE or provide their own CodeSys version, you can expect the terminology to match exactly what I just described. However, two of the biggest players in the market, Siemens and Rockwell Automation, use their own terminology. Siemens implements the standard quite closely in TIA Portal and CMotion. They support function blocks and functions just like the standard. The main difference is the program. Siemens calls these organization blocks or OBs. Rockwell Automation is the most unique. While they support the concept of the IEC program, the structure is different. In Studio 5000, a program is a container that holds tags and logic, but the actual code is split into multiple objects called routines. For usable logic, Rockwell uses add-on instructions. They work almost exactly the IEC function blocks, so they have inputs, outputs, and internal memory. However, Rockwell does not provide a direct equivalent to the IEC function. To achieve that behavior in Rockwell, programmers often have to use subroutines or global add-on instruction instances as workarounds. And regardless of this naming difference, the architecture remains the same. If you want to practice declaring these POUs yourself, you can check out my courses on Udemy or my book PLC Programming for Beginners on Amazon. Now we are going to explore the second major aspect defined in the standard, that is the data model and variable declaration. A PLC program is fundamentally the manipulation of memory. To do this reliably, we must understand the technical specifications of the data types defined in the standard. A variable is a symbolic name associated with a specific memory location. When we declare a variable, we are providing the compiler with two critical pieces of information. Number one is the data type, how many bits of memory to allocate and how to interpret them. And second, the scope, which parts of the program are permitted to read or write to this memory. In this video, we are going to explore the elementary data types supported and defined by the standard. Choosing the correct one is critical to prevent overflow errors and to optimize the memory usage in your application. So let's start from the classic, most fundamental variable, the boolean. This represents a single binary logical state. It can only have two values, 0 or 1, also called false and true. While logically it occupies a single bit of memory, most systems allocate a full byte or 8 bits for addressing efficiency. Then we have bit string types. These values are the concatenation of multiple bits. We have the byte that is made of 8 bits, the word that is made of 16 bits or 2 bytes, the D word or double word made of 32 bits or 4 bytes, and the L word or long word made of 64 bits or 8 bytes. Although they occupy the same memory space as integers, they are not interpreted as numerical values. Instead, they are treated as raw bit patterns. These types are essential when you need to pack multiple Boolean flags into a single variable, or perform bitwise logical operations using masks. Then we have integer types, used to represent whole numbers. The key distinction among different types are the memory size and whether or not the type is signed. Signed integers can represent positive, negative, or zero numbers, while unsigned can only represent zero and positive numbers. All unsigned types in the IEC 61131-3 standard start with the letter U. So, starting from the smaller sizes, we have the short integer that occupies 1 byte, SINT for the signed version that can range from -128 to 127, and the USINT for the unsigned version that can range from 0 to 255. Then we have the 2 bytes integer, int for the signed version and uint for the unsigned one. The 4 bytes double integer, dint for the signed version, udint for the unsigned one, and the 8 bytes long integer, lint for the signed version, ulint for the unsigned one. The choice of the correct integer requires caution. You should use a type that is large enough to avoid overflow during calculation or representation of the maximum value that you require, while considering also memory efficiency. Also, mixing signed and unsigned integer in calculation requires caution, as implicit conversion may lead you to unexpected results. Dint and udint are very common for general purpose use and provide a good enough range for most applications. Then we have the real types, that are used to represent numbers that may have a fractional part, using a floating point format, for which there are 2 versions. The real variable, a 32-bit floating point single precision variable with approximately 7 decimal digits of precision, and the long real variable, 64-bit floating point double precision variable with approximately 15-16 decimal digits of precision. A crucial data type in automation is the time variable. Since many temporized actions or sequences may occur in a PLC program, using times to set up timers and delays is crucial for a PLC programmer. The time variable represents a time interval or duration. It is declared using the literal syntax t#, followed by a value and a unit of time. D for days, H for hours, M for minutes, S for seconds, and MS for milliseconds. For example, t#2s indicates 2 seconds, t#500ms indicates 500 milliseconds. Internally, most PLC systems implement the time variable as an unsigned double integer that stores the duration in milliseconds. You should know that whenever you need to carry out some calculation using time variables, you can add them, you can subtract them, but under the hood you should know that they are unsigned double integer most of the time. Other less used types of variables are used to represent a time of day, a date, or a combination of both. You may find that manufacturers implement their own version of this rather than following what the standard provides as a guideline. So you should not, in my opinion, waste too much time learning how the specific time of day or date and time is implemented in the standard. Since most of the time, if you're working with a specific manufacturer PLC, you may find a different implementation. Then there are the string variables that are used to represent sequences of textual characters, useful for setting some text to be displayed or to carry out some encoding for communication protocols. The most commonly used is the string type, that is a variable length variable in which each character is encoded inside a single byte. Beyond these standard data types, the IEC 61131-3 standard supports derived data types, allowing programmers to create arrays that are index collections of variables of the same type, or structures, collections of potentially different data types grouped under one single name. Choosing the right data type ensures your machine can calculate values correctly, but knowing what data to store is only half the battle. You also need to control who can see and interact with that data. If you want a comprehensive list of the variable types supported by the standard, among other informations, check out my book, PLC Programming for Beginners, on Amazon. A link is in the description. Now we will cover the scope or visibility of variables supported by the IEC 61131-3 standard, a crucial concept that establishes boundaries on who can read or write a certain variable by promoting encapsulation that is fundamental for modular software design. Let's start with local variables. These variables are defined within a Program Organization Unit, or POU, and they are private to it. The POU itself can access, read, or write local variables, but they cannot be accessed externally. This enforces data hiding, a key principle of modular programming, ensuring that the internal workings of a POU cannot be unintentionally or intentionally affected by other POUs. As shown in the previous video, local variables will retain their values between execution scans if the POU is a program or a function block, and instead, if the POU is a function, they will be reinitialized at the next call of the function. In codesys, they can be declared within any POU declaration between the var and endvar keywords. Input variables act as parameters that can be passed to the called POU from a calling POU. They are inputs, so they can be written from outside the POUs in which they are defined and can be only read from inside the POU. They are useful to provide set points, enable signals, configuration parameters, sensor readings, or more to a function block or a function. In codesys, they can be declared within any POU declaration between the var input and the endvar keywords. If they are not present in the declaration of your POU, you can add them yourself. Output variables instead define results or static information that are produced by function or function blocks to the outside. They can be written only from inside the POU in which they are defined, and they can only be read from the outside. In codesys, they can be declared within any POU declaration between the var output and endvar keywords. Input-output variables are a little different. They are variables that are passed to the POU by reference. Instead of copying the value, the POU receives the memory address, the pointer of the original variable that is supplied by the caller. In this way, both the calling and the caller POU can read and write the specific variable that is passed as input-output. They are particularly useful to pass big structures, big data to function block, and specific flags that can be either written from inside or from outside a specific POU. In codesys, they can be declared within any POU declaration between the var in-out and the endvar keywords. Then there are global variables that in codesys are declared outside of a specific POU. This is true also for other PLC manufacturer systems, and they can be accessed from any POU within the entire project. They can be either read or written by any POU. And they provide a mechanism that is very simple to share data across different program units, but be careful in overusing them because it undermines encapsulation and modularity of your project. Use them for really system-wide global settings, and it's typically better in my opinion, to avoid using them if not strictly necessary. Prefer using inputs, outputs, and input-outputs for blocks instead of global variables to ensure better structure, code reuse, and maintainability. To define global variables in CodeSys, you need to place them inside a global variable list object in the device tree of your CodeSys project, and the default project should already have one named GVL, but if you want to add a custom list, right-click on Application, select Add Object, click Global Variable List and choose a name from your list. Then, by opening the list, you can define your global variables between the keywords var global and var. We have covered the data model in the IEC 61131-3 standard, describing all the data types and scopes supported in the standard. If you want to practice declaring these variables yourself, you can check out my courses on Udemy or my book PLC Programming for Beginners on Amazon. Now we are going to explore the third major aspect defined in the IEC 61131-3 standard that is probably the most important: the programming languages. Originally, the standard introduced 5 languages, 2 textual and 3 graphical. However, the instruction list language was deprecated in the 3rd edition of the standard due to its poor readability and higher risk of error. Therefore, we will focus on the 4 remaining languages, examining their origin, features, strengths, and weaknesses. First, we have the most widely recognized and historically significant language, ladder diagram. Ladder diagram is a graphical language designed to mimic the schematic drawings of hardwired relay logic circuits. It was created specifically to ease the transition from physical relays to PLCs, making it immediately accessible to electricians and technicians familiar with electrical diagrams. A ladder diagram program is divided into horizontal lines called rungs, and each rung acts as a line of code, executing sequentially from top to bottom. Each rung connects 2 vertical power rails, creating a conditional flow of power from left to right, by placing contacts to evaluate conditions and coils to drive output. Ladder diagram is highly intuitive for anyone with electrical background. You do not need to be a computer scientist to read and troubleshoot a ladder program. It allows for excellent visualization of discrete Boolean logic, making it the industry standard for machine interlocks, safety circuits, and process logic, where diagnosing a stop machine quickly is the priority. It is very widely spread and used in many industries and has been for decades the industry standard for PLC programming. However, ladder diagrams become cumbersome when managing intricate algorithms, complex mathematical calculations, or string manipulations. It is significantly less compact than textual languages, and furthermore, it struggles to integrate with modern software engineering tools like version control system and code comparison tools. On the other end of the spectrum, we have structured text. This is a high-level textual programming language with syntax derived from classical languages like Pascal and C. Structured text is the most powerful and flexible language in the standard for implementing complex algorithms, mathematical functions, and data processing. It is far more compact than any graphical equivalent. Because it is text-based, portability between different hardware platforms is much easier, and it also integrates better with modern development workflows such as version control, continuous integration, and automated code generation. It offers a very fast learning curve for those with prior IT or computer science experience. Conversely, ST can have a steeper learning curve for personnel without a traditional programming background. It is generally less accessible for electrical maintenance staff and electricians. Additionally, visualizing Boolean logic for troubleshooting purposes is often less immediate than looking at it in a graphical language such as ladder diagram. Then we have a function block diagram. This is a graphical language where logic is represented through a network of interconnected blocks. Unlike ladder, which visualizes power flows, FBD visualizes signal flows. FBD provides an intuitive representation of how data moves through a system. It excels in applications involving signal processing and continuous control loops such as PID control, motion control for calling motion control blocks, where visualizing the input-to-output transformation is important. But in simple Boolean logic, it can sometimes feel less efficient alternative to ladder. In very complex network with many feedback loops, connections can become very messy. And moreover, it is very similar to ladder for a lot of things, and it is often criticized for being a less popular alternative than ladder. So many people say that you should stick to the more adopted and more used language, that is ladder diagram. And finally, we have a sequential function chart. This is a unique graphical language designed specifically to structure sequential processes. It is based on the GraphSet standard and resembles a state machine diagram. It is excellent for visualizing distinct operating states, and it provides a clear, high-level overview of the process flow, making it very easy to diagnose exactly when and where a machine is stopped in its cycle and where it is running. It is important to note that SFC is a structural language. The detailed logic in the steps and transition must be implemented using other IEC languages, typically structured text or ladder. Furthermore, experienced programmers can often implement state machines entirely in structured text to gain more flexibility than the rigid SFC structure permits. So, which language should you choose? In the modern industry, the choice usually comes down to ladder diagram versus structured text. However, you will find often that the choice is already made for you. Your company, your customer, or the specific industry standards will likely dictate the language based on legacy support, market preference, or maintainability requirements. You must understand that the reason behind language selection is rarely purely technical, and it is often organizational. If you work for a process end user, where the priority is maximizing uptime and troubleshooting is done by maintenance technicians working multiple shifts across different lines, you will likely use a ladder diagram. And if you work in an R&D department of an OEM building standard complex machinery and you need to support a massive install base with efficient updates, you will likely work with structured text. The trend in industrial automation is slowly following the IT world. It is lagging behind maybe 10-15 years, and structured text is becoming increasingly favored for complex data-heavy applications, while ladder diagram is still maintaining its dominance in many industries and geographical locations. This section concludes our video course on IEC 61131-3. If you wish to dive deeper into these languages and start coding, check out my book PLC Programming for Beginners, available on Amazon.